Now we're thinking about something a little bit different, electric force. And like any force, you can think about its direction and its magnitude. Direction is pretty straightforward. It's something that you've heard before with the old slogan, opposites attract and likes repel. There are two different types of force. Thanks to Benjamin Franklin, we call them positive and negative. So, for example, let's say we have two charged objects with the same type of charge, both positive. Opposites attract, likes repel. Likes repel, so two charges of the same type, both positive in this case, repel each other. B feels a repelling force from A. B is pushed away from A, and the force from A on B pushes B this way, away from A. And similarly, A feels a force from B. B is repelling A. B is pushing A away from B. Force from B on A repels A away from B. And then opposites attract, two different charges of opposite type. Here's a negative and a positive now. They'll apply attracting forces to each other. And so the force from B on A pulls A toward B, attracts A toward B, and the force from A on B pulls B toward A, attracts B towards A. Notice something about what I've just said here. The pattern that you see here is a pattern for a Newton's third law pair of forces. These two forces are a third law pair. These two forces are a third law pair. They have all the characteristics of a Newton's third law pair. They're both the same type of force. These two forces are both electrical repelling forces. These two forces are both electrical attracting forces. And like any Newton's third law pair, they point in the opposite direction. Point opposite direction, point opposite direction. And like any pair of Newton's third law partner forces, look at the pattern here. The source of one force, right, this force comes from A. The source of one force feels the second force. And the source of this force comes from B, receives the other force. In a Newton's third law pair, it's always the case that one of the forces is from the first thing on the second thing, and the other force is always the second thing back on the first thing. Same here. Here's a force from A on B. Here's a force from B on A. A is a source of one of the forces, this force, and it's the receiver. It's acted upon by the other force, and likewise for B. Right? B is the source of this force, and B is acted upon by this force. So, being a Newton's third law pair, those two forces have the same magnitude. The force from A on B and the force from B on A are the same size. And it turns out that in our rule for the magnitude of an electric force, that third law equality of magnitudes is built right in to the equation. Here's the rule for the force from one thing on a second thing. Looks like this. K is some constant that you can look up. Its value is about 9 times 10 to the 9th, and then the rest of the denominator is a product of two charge magnitudes. Magnitude of the charge that is the source of the force, and then magnitude of the charge that is feeling that force, a magnitude of the charge that is acted on by that force. 1 is the source of the force, 2 is the thing that feels the force. That's the numerator, and then the denominator is square of the distance between the two charged objects. Well, if we look at the force closely related to this, the force that 2 applies back on 1, what do we see? There's K times product of two charge magnitudes, and the first, remember the first slot here goes with the magnitude of the charge from the source. In this case, it's 2 acting upon 1. 2 is the source of the force, so charge 2 goes here. And then magnitude of the charge that is feeling the force. This is a force acting on 1. Thing 1 is feeling the force, so the magnitude of its charge goes here, divided by square of the distance between the two charges. But look, this numerator is k q1 times q2. This numerator is k q2 times q1. Same result. Flipping q1 and q2 around doesn't change the number you come up with. So the magnitude of this force is the same as the magnitude of this force, just like it should be in a Newton's third law pair. And the important point here is that this is true no matter what Q1 and Q2 are. Might be the case that Q1 is a million units of charge, and it might be the case that Q2 just has 1 unit of charge. But even in an extreme difference like that, the force from 1 on 2 will be K, magnitude of that charge, which is a million, times magnitude of the other charge, which is 1, over square of the distance. And then flip it around, the force from 2 back on 1 has a magnitude equal to K, magnitude of the source of this force, magnitude of Q2, so that's 1, times magnitude of the charge that is feeling the force. For this force is felt by, this force acts on Q1, magnitude of a million, divided by square of the distance between the two charges. And there you see, again, even though the two objects have very, very different amounts of charge, they each feel the same amount of force. They each apply the same amount of force to the other, because those two forces are a Newton's third law pair. Now let's look at one thing about this rule for the force, the electric force between two charged things. let's say you leave those two charges alone. You just move, you don't add any charge, you don't take away any charge, but you move the two charged objects around. So, for example, you might start off with the two charges some distance apart, and in that case, let's say that the force that each applies to the other force that one applies on two and the force that two applies on one, they're the same size because they're a Newton's third law pair. Let's say that in that case, the force is 4 times 10 to the minus 4 newtons. Now, you take those two charges and you pull them farther apart so that now they're twice as far apart as before. Right? D has increased, so the denominator of this fraction has increased, so the fraction overall is smaller. The force is weaker. So exactly how much weaker? When the new distance between the charges is twice what it used to be. Well, look at what we have here. We didn't change the charges, so nothing in the numerator has changed. The only thing that varied, the only variable on the right-hand side is d squared. So what we really have here is force equal to constant stuff divided by d squared. We have inverse proportionality. We have one variable equal to constant stuff divided by another variable. That is, the magnitude of the force is proportional to 1 over d squared. And we know how things work in inverse proportionality. When one of the proportional variables changes by some factor, the other changes by the inverse of that factor. So in this case, we want to figure out the new value of the force. In other words, we want to figure out the factor by which force changed. Well, that's the inverse of the factor by which d squared changed, because d squared is the variable that's inversely proportional to f. If we know the factor by which d squared changed, we know that f changes by the inverse of that factor. So how does d squared change? That's easy to figure out. You just square this whole equation. So the variable called d squared changed by a factor of 4. The new value of d squared is 4 times the old value of d squared. So the variable called d squared changes by a factor of 4. The thing that it's inversely proportional to, the strength of the force, changes by the inverse of that factor. The new value of the force is just 1/4, the inverse of that factor, times the old value of that force. So the old value was 4 times 10 to the minus 4th. 1/4 of that is just 1 times 10 to the minus 4 newtons. Notice one thing that happened in all this. It'll be a useful thing to remember. It'll come up a lot. So remember it. What we did in this example was double the distance between the two charges. When you doubled the distance, the force was cut down to 1/4 of what it had been previously. So when you double the distance, new distance is twice the old distance. That means the new force is cut down to 1/4 of what it had been. The new force is just 1/4 of the old force. And you could do this proportionality reasoning the other way around, of course. Let's say you have a situation of two particles, let's say 2 centimeters apart. That's their distance, and then there is some force. Some force acting on them, and then you move them closer together so that now the force is larger than it was before. Now the new force is 2 times larger than the old force. Right? The new force is 2 times larger than the old force. So what is this new distance? Move them closer together. Well, let's see. Use the same rule. Our inversely proportional variables are force and square of the distance. So if one variable changes by a factor of 2, the other variable must change by a factor of 1/2. In this case, force changed by a factor of 2. So the other variable, which is d squared, changes by the inverse, changes by a factor of 1/2. Right, the new value of d squared is 1/2 times the old value of d squared. And of course what we're looking for is the new value of d. What we're looking for is just the plain old distance in the new case where I've push the two charges together so that now there's twice as much force. Well, all you have to do is solve this equation for d2. And the easiest thing to do is just take the square root of the whole equation. So d2 is just the square root of this, 1/square root of 2 times the square root of this, which is just plain old d to the first power. D in the first case was 2. So the new value of distance is 2 divided by the square root of 2, which will come out to about 1.4 centimeters. So to make the force twice as strong, we didn't have to cut this distance in half. We only cut it down from about from 2 to about 1.4. Okay, the other thing I wanted to show you was a more complicated situation where you don't just have 2 charges interacting with each other, but 3 charges. Now, to keep it relatively simple, we'll say they're all in a row, just along one dimension, and they're all separated by equal spacings. So here's a negative charge, and a positive charge, and another positive charge. And this distance between these charges is the same as the distance between these charges. I'll call these charges A, B, and X. And we'd like to know something, we'd like to see what we can figure out regarding the net force on X. Well, whatever it is, we know that that net force is a sum of the force from A on X plus the force from B on X. Let me write that again over here. Net force on X is a sum of the force from A on X plus the force from B on X. And it's helpful when doing the algebra related to all this to have a standard unit for force. So the thing that makes all this easier is to say that the force on some particle, like X, from one unit of charge one step away, we'll call that force a magnitude of just plain F. So for example, in this case, the force from B on A, or the force from B on X, excuse me, the force from B on X has a magnitude that we call just plain F, because B is one unit of charge and B is one step away from X. F is the name we give to the magnitude of a force from one unit of charge one step away. So that's the magnitude, and the direction of this force is in the positive direction, because these are like charges, so they repel each other. In particular, B repels X. B pushes X away from B, so X is being pushed to the right. X is being pushed in the positive direction by the force from B. So this force, the force from B on X, points in the positive direction. Now, for the force from A on X, notice that A is twice as far from X as B is. So when we switch from considering this interaction to considering this interaction, we have doubled the distance. And we know that when you double the distance, you cut the strength of the force to 1/4. So the strength of the force from A on X is 1/4 as strong as the force from B on X. So the magnitude of this force from A on X is just F over 4. And what about the direction? A and X are opposite signs, so they so they attract each other. Opposites attract. In particular, A attracts X toward A. A pulls X toward A. The force from A on X pulls X to the left. The force from A on X points to the left. And we're calling that the negative direction. So then the net force on X is the sum of these two forces, which will just be 3/4 F. In other words, the net force that X feels would have been just plain F if B were the only force, right? If A were not around, if B were the only other charge applying a force to X, you'd have a force from one unit of charge one step away, and we call that a force with magnitude X. But now adding A into the picture turns out to make the net force on X a little bit weaker than it would have been from B all by itself. Only 75% as strong as the force from B itself. Okay, one more example. Take the same three charges, but now let's look at the net force on the one on the left. So those are, again, we want to figure out the net force on X. And again, it's a sum of the force from A on X plus the force from B on X. A is 1 unit of charge, 1 step away from X, so the strength of A's force on X is what we call just plain F. And in which direction does that force point? It points to the right, the positive direction, because X and A are opposites, so they attract each other. In particular, A attracts X. A pulls X toward A. A pulls X in the positive direction. The force from A on X is in the positive direction. And that's exactly the same for the force from B on X. Again, when you look at the interaction between X and B, you've got opposite charges, so they attract each other. B is applying an attracting force to X. B is pulling X toward B. The force from B on X is a rightward force, a force in the positive direction. And similar to the previous case, B is twice as far from X as A is. So if you say that the distance between X and A is just plain D, and then of course the distance between A and B is also D. The distance between X and A is D. The distance between X and B is 2D. Again, you've doubled the distance, so you've cut the strength of the force down to 1/4. This force is only 1/4 as strong as this force, which was twice as close as this, because A was twice as close as B. So when you add them all up, you come up with a net force on A that is equal to 5/4 times F. The net force is a little bit stronger. The net force on X is a little bit stronger than it would have been if A had been the only other charge in the picture. If A was the only charge besides X, the net force on X would have been just plain F pulling to the right. But now you add this second charge, and as a result, the net force is a little bit stronger. It's 5/4, 1 1/4, pulling X to the right. Okay, so that's where things stand. And then in our meeting, we'll also talk a little bit about electric field, closely related to electric force, but different.